So today, of course, I am not going to do anything new. I think I am more or less finished, except for a review and just telling qualitatively what are the other theories that are possible. We have mainly described the many electron problems. So, in particular Hartree-Fock, which is of course the best uncorrelated theory. So, this is the reference point from where all the electron correlations start. So, then we discuss the electron correlation as the important topic, and in particular we developed perturbation, the algebraic as well as diagrammatic, and of course CI, the configuration interaction, as the two major methods of electron correlation. Of course, there are several things to do. So, our interest has been mostly on the energies, but I must tell you that as you go forward, we also need to learn how to get not only energies, but also energy derivatives. And this is something that we have not covered in this course. How do you get energy derivatives with respect to some external perturbation, external field or perturbation? This is a very important topic, and this is often called the response. This is something we have not covered. That means, how does the energy change if I give an additional field like electric field, magnetic field? This is very important because electric field change gives you dipole moment, right? If you have second order change, it is called polarizability and so on. So, these are also very important to calculate analytically. So, I must mention the numerical calculation is very easy, because you just put an external electric field, your one particle potential changes, you keep doing whatever you want to do and take a numerical derivative. What is of importance is of course analytical derivative, analytic derivative, and this is something that is a very important part of quantum chemistry. Not only external field, equally important or even more important are the nuclear coordinates. And this is a very part that we discussed, that if I change the nuclear coordinates, then of course my Hamiltonian will change, because the external potential changes. How does the energy change? And these are basically known as, these derivatives will be known as the gradients and the Hessian. Many of these are used for geometry optimization. Why I am saying? Because in quantum chemistry, a very important part is to optimize the geometry of a molecule. So, what do you mean by optimization of geometry? If you calculate the potential energy surface like a diatomic molecules, we have to find out where it is minimum, right? The simple hydrogen molecule, if I do it correctly. So, this is the point which is 1.4 atomic unit or whatever for H2 molecule, it is a minimum. So, for a complex polyatomic molecule, we have to find out where the equilibrium geometry is. So, what we need to do is to calculate this energy, which I call potential energy. I hope all of you remember what is the difference between V and E electronic. What we have done, the calculation is E electronic, because in the Hamiltonian we have not added the nuclear repulsion term. So, if you add the nuclear repulsion term, which is a constant, so it will not change anything, you get the potential energy. So, for gradient it is very important, because this part is also a function of nuclear coordinates. Okay. So, when I do the gradient, I have to calculate del V del R, all R, let us say there are n number of R's for nuclear coordinates, which are basically degrees of freedom, vibrational degrees of freedom, like 3n minus 5, 3n minus 6. Then you know that for a minimum, each of them has to be 0. So, this is a very important equation. So, what we mean by analytic derivatives is to calculate these analytically and then set an equation that this is equal to 0. Okay? And then we have to see whether it is maximum or minimum by looking at the second derivatives. and checking the second derivative matrix, which is basically called Hessian. So, this is gradient and this is Hessian. Second derivative matrix I take with respect to one R and another R. So, Ri Rj, this is a matrix as you can see as a function of Ij. This is called Hessian matrix, and the trick is that if you diagonalize this matrix, you get the eigenvalues. If those eigenvalues are all positive, then it is called minimum. These eigenvalues are essentially the frequencies. You know, many of you might have heard IR frequencies. This is another way to calculate. This is the infrared because I am changing potential energy with respect to coordinates. I calculate those frequencies. If they are all positive, then if they are all positive, then it is called the equilibrium geometry. And of course, there may be negative frequencies. If one of them is negative, two of them negative, you will get different states which are actually called transition states. You know, many of you will be using the transition states. So, we have not done in great details, but I thought today I will just tell what are the other things that we have to actually do apart from calculation of energies. So, what we have focused in this entire exercise is to calculate the energies, okay? But the gradient and Hessians are very important part along with other external field response, and this in general is called response approach. So, this is a very important part. How do you calculate this apart from the energy calculation? Whichever method you pick up, in the same method you have to do consistently this. We have of course discussed within the energy important problem of size consistency in great details. When is a theory size consistent? When is theory not size consistent? And in particular, we discussed the Hartree-Fock, that Hartree-Fock itself may not be size consistent. When even a restricted Hartree-Fock or Hartree-Fock, when a closed shell molecule fragments into open plus open, it is not size consistent. However, if they goes into closed plus closed, it is size consistent. But then even if it is size consistent, if I do approximate Ci, the size consistency can go down. So, in particular, we have taken a system of H4 getting into H2 plus H2. So, with an example, we showed that H4 can go to H2 plus H2 correctly in the case of the restricted Hartree-Fock, but here this correction breaks down if I do an approximate Ci, and in particular we discussed DCi. I hope you remember this particular model problem. This model problem was essentially a Hartree-Fock 1 bar. Note that whenever 1 bar will be used, please remember it is a spin orbital with 1 as the special orbital, beta as the spin orbital, spin. So, that is something that you should have no confusion. So, this is just called chi1, chi2 in our nomenclature, where chi1 is 1 alpha, chi2 is 1 beta. So, that is the spin orbital, okay. So, please be careful even whenever we ask, be careful of the symbols. So, if I am saying chi1, chi2, then of course, this will be chi1, chi2. If I am writing in terms of special orbitals, this can be written 1 bar, and then 2 bar becomes chi3, chi4. So, a very simple minimal basis problem where this is orbital, special orbital 2, this is special orbital 1, we have done in great detail, and in particular we discussed the wave function, the DCi wave function, which is 1 bar plus C 2 bar. Remember, this is a DCi wave function, and this is actually full Ci for this problem if we restrict ourselves to a symmetry adapted state. So, let me just quickly tell you why. As you know that this symmetry is sigma g. All of you know for hydrogen molecule, when I do this, it is a sigma g, 1s A and 1s B symmetric combination, and this is called the sigma u, which is anti-symmetric combination, okay. So, if I do a 1 electron excitation from G to U, which can be a part of the Ci, SDCi, full Ci, the 1 electron excitation will lead to a symmetry which will be G into U, because one of the electrons will be in sigma G, one will be in sigma U. So, that will become a small u symmetry, okay. Remember that this is sigma G square. So, sigma G square has a group theoretic symmetry which is singlet sigma G, capital sigma g. I hope all of you are more or less familiar that the capital sigma is for the molecular term symbol, small sigma is for the orbitals, right. So, this you have done in MSc itself. So, if I restrict only this wave function to singlet sigma g, then you can imagine I cannot have any function which is singly excited, because it will involve one g and one u. This will then become u state. I am interested only in g state. Further, of course, I am interested in capital sigma state, which will be always generated if I have 2 sigmas, so no issue. Further, I am interested only in a singlet state. Okay. So, the only state that is possible is 2 2 bar, which is doubly excited, because if I have put both the electrons in sigma u, then sigma u square also is a singlet sigma g state with a higher energy normally. If you look at these two determinants, they are higher energy, but your actual ground state energy is a combination of these. So, this will have a larger dominance, this will have a lower dominance for this kind of states. Okay. But of course, as I discussed for the hydrogen molecule, if you stretch this apart, then both these orbitals come very close, and then of course, that is the reason RHF breaks down, because they become nearly degenerate. So, if I go around this part, when R tends to infinity for hydrogen molecule, these two almost come together, and both sigma g square and sigma u square become almost equally important. So, that is a failure of the RHF, and eventually all the theories have to be geared to take this. So, we have discussed the DCI problem. We also have discussed how to solve the DCI equations iteratively. So, solution of particularly DCI equations iteratively. Of course, DCI or any CI can be solved as an eigenvalue equation. So, let us not forget, but we iteratively essentially means that we do not want to solve the entire eigenvalue problem. We want to look at only the ground state or the lowest root in an iterative manner, and very often we have started with an A correlation expression in terms of E correlation and set E correlation equal to 0 as the first guess, and then you continue so this also we have discussed very elaborately. So, I just wanted to mention this. I should now mention few of the other theories for energy calculation which I mentioned. Alright, so perturbation I have already told you that we have discussed yesterday also in great detail, diagrammatic and connection with algebraic, except that we have not proved the link cluster theorem. We have simply used the link cluster expansion of Goldstone, and yesterday we gave you a model problem. I hope you remember, practice problem of MP4. So, please try to do. I have given a 4th order diagram. So, do not say that the 4th order is outside the syllabus. I have given the diagram yesterday. If I give a diagram, you should be able to write the algebra with all the Hugenholz rule. There are only Hugenholz diagrams is what we have done. So, you should be able to write the algebra with the sign and everything correctly. Okay. Alright. So, apart from perturbation and CI, we said that we are going to cover, at least mention the names of a few more methods. So, one of the important methods is what is called the MCSCF. I think the name itself is clear. It's multi-configuration self-consistent field theory. Okay. So, this is known as the multi-configuration self-consistent field theory. So, let me just explain what it is. So, this is the full form of this. Self-consistent field is already you know, that is a Hartree-Fock, where for a single determinant you try to get the best spin orbitals. Okay. You also know what is multi-configuration theories in CI. CI is a multi-configuration expansion. So, this is, as the name suggests, is a mixture of CI and Hartree-Fock. The spirit, Hartree-Fock is optimizing the orbitals, right, that is self-consistent field. CI is optimizing the coefficients of an expansion. If I have a linear expansion, how do I optimize the coefficients? So, in MCSCF you do both. So, you have a wave function which is a combination of determinant, first linear combination, of determinants, and these determinants have to be chosen carefully. Then you optimize the energy with respect to both the linear expansion coefficient and the orbitals involved in the determinants. Not just one determinant, there are many determinants, all the orbitals involved in the determinant. You can clearly see that this goes much beyond Ci. This of course is beyond Hartree-Fock because I have a multi-configuration function, and it can be a very, very accurate method, because depending on number of determinants, there are many orbitals. All the orbitals I am optimizing. Just like in Hartree-Fock, you remember, I wrote energy as a optimized with respect to orbitals, right? Orbitals essentially could mean LCA coefficients, orbital expanded in a basis, so then coefficients are optimized, but essentially orbitals. And in Ci, it was a reverse problem, orbitals are fixed. If you remember the standard Ci that we did, we always went with a basis of orbitals, which was Hartree-Fock orbitals. With those Hartree-Fock orbitals, we constructed Hartree-Fock determinant, singly excited, doubly excited, and we only changed the coefficients. So the equation was only to get the coefficient which is an eigenvalue equation. Okay, we have again done this. You construct the H effective matrix for the E correlation where the first term is 0, and then all matrix elements of H minus E Hartree-Fock with respect to all the determinants. But determinants are fixed because orbitals are fixed in Ci. Only the coefficients you change. In this case, we are doing both. So for example, so obviously in such a case, we have a restriction that we can't take such a large Ci because there are too many determinants. If I have to do this, it's really a no-go from the beginning because it's too complex a problem. So what we do is to actually take problems where it is required. So one of the problems is precisely what I have discussed just now, that I have a situation where hydrogen molecule, I mean hydrogen is just an example, stretched. So if I stretch it, the configuration sigma g square and sigma u square will be nearly same in energy. Okay, they may not be degenerate. They may be degenerate only at the separation point, but if I stretch, they will come closer and closer. So basically, if this is the equilibrium sigma g and sigma u, as you go forward, this will go down, this will go up, and something like this. Okay. So this kind of system is not degenerate, but they have a name in quantum chemistry which is called quasi-degenerate. The quasi essentially means that it is nearly degenerate, not exactly degenerate. Now, in all systems and including degenerate systems, I need to construct the wave function not as I discussed, the Hartree-Fock fails, but I must need to construct the wave function phi naught as some C naught sigma g square plus C1 sigma u square. Right? In a small model, this is exactly full Ci, 1 1 bar, 2 2 bar, except the C naught is 1. I mean, normally we have said C naught is 1 for intermediate normalization, but that's unimportant. So if I have only 1 1 bar and at minimal basis this is then 2 2 bar, it's of course full Ci. But if there are many other bases, it is a part of the double Ci, and there may be many other double Ci coefficients. But knowing the physics here that only these two configurations are important, that is 2 electrons here and 2 electrons here, I can do a much better job than just doing a Ci. Note again, in a minimal basis, this is exact. Okay, I again repeat for a hydrogen molecule. But if there are many other orbitals, then it is not exact. So to do exactly even dCi, I need to take many configurations, correct? I may have to take even singles for full Ci, because there may be another orbital with G symmetry, where I should be able to excite, because G into G remains G, right? Here it was only G and U, minimal basis, so I can't do. So, in principle the problem may be very large even for hydrogen molecule if there are many number of orbitals, but I know that only these two configurations are important, the rest are not important. In such a case, I should be able to write only as a combination of these two determinants, and then not only vary these coefficients just like in Ci, but also vary these orbitals themselves 1 and 2. So, I would vary C0 and C1 as well as 1 and 2. Remember the sigma g and sigma u normally when I do Ci, I have taken from a Hartree-Fock calculation and fix it. But now what we are suggesting is that anyway this is an approximate calculation. Let's not just take Hartree-Fock 1 and 2, let's also try to re-optimize 1 and 2. So, the reason it will change is that now that we are optimizing the orbital 1, it is being optimized not just for sigma g square, that was the Hartree-Fock, but in the presence of another determinant. So, there will be a coupling term, and because of that the orbital 1 will change. Similarly, orbital 2 will change, the coefficients will change of course when I vary. So, it is a very complex problem, and this is exactly what is MCSCF, multi-configuration SCF. Multi is here 2, that 2 can be 3, 4, 5, but in general you do not do a multi-configuration SCF with 1000 configurations, because then there are so many orbitals. The orbital optimization itself is a nonlinear optimization, as you know, because orbitals are the exponential something quadratic, even Gaussian or whatever exponential term. So, they are extremely difficult to optimize. Hartree-Fock we could do because there is only single determinant. So, obviously, if there are 1000 determinants, you can't optimize the coefficient and orbital, they are very, very expensive. So, MCSCF has to be used judiciously. Those who will do MCSCF, remember, should be done for a particular problem where a few configurations are important. So, do not do a real CI, because CI you are taking everything. Even in CI, of course, you do selection. I told you by looking at the energy denominator, you can select determinants, amplitudes, but at least here I know that a few configurations are important. Okay, in such a case, you can actually do MCSCF. It gives a very, very accurate results. Many times these configurations are chosen by looking at active orbitals, and I will tell you what is an active orbital. So, let us take a problem of more than 2 electrons, so where it will be relevant. So, let us say that these are my occupied orbitals and this is the line, these are my virtual orbitals. This is not an orbital, it is just a line separating the occupied and virtual orbitals. So, this is my LUMO, this is the HOMO, and of course, I have many other orbitals here. So, I have let us say 10 electron system. Okay. So, up, down, whatever. Now, and then there are LUMOs. So, I can generate many configurations by exciting electrons from here to here. Okay. Question is, I want to do an MCSCF because this gap between HOMO and LUMO has become very, very small. So, it is exactly the similar problem that the gap between HOMO and LUMO has become small. So, there may be other configurations which are important. So, you may decide then to choose what are called active orbitals, which have to be mixed. So, if you ask me what are the active orbitals in this problem, the active orbitals which were mixed is sigma g and sigma u. In this case, there are 2 active orbitals. So, let us say that I choose similarly one active orbital from here, one active orbital from here, and then I construct all possible determinants where the electrons, active electrons are put within these orbitals, within these 2 special orbitals. So, let us say I choose active orbitals as HOMO and LUMO. So, 2 orbitals, how many spin orbitals? 4 spin orbitals, correct? I do not want to change this. So, all my configurations will have these frozen, these 8 electrons. So, these are not my active. So, active electrons are also only 2. Okay. Now, without looking at the symmetry, how many determinants I can form between these active orbitals? So, that means I am free to excite one of the electrons here, 2 electrons here, whatever. But everything that I do is just between these two special orbitals and involving these two electrons. These 8 electrons are fixed. So how many determinants I can make? Does everybody agree? You have 4 spin orbitals, 2 electrons, so you have 4c2 without looking at the symmetry right now, because we don't know the symmetry of the orbitals. They may have the same symmetry, so you should be able to excite, okay. So in general, I have 6 electrons, so if 6 determinants, so if I make a wave function which is now a linear combination of these 6 determinants, okay. How did I choose these 6 determinants? By first choosing the active orbital. Remember, if I say this LUMO plus 1 is also very close to LUMO, then I can expand my active orbitals as HOMO, LUMO, LUMO plus 1. So active orbitals are essentially orbitals which are near degenerate or quasi-degenerate. So look at the degeneracy of within the HOMO, within the LUMO, and between HOMO and LUMO, and choose the active orbitals, okay. Of course, if it is only within the HOMO, there is nothing to choose, because that is already filled. So it has to involve LUMO, of course, the unoccupied orbital, not only LUMO, LUMO plus 1. So if I have one more orbital, this would become 6, this and this, and then my number of the 6 active, so it will become 6c2. I can also say that HOMO minus 1 is also very close. Then what will happen? I will have this, and maybe one more. These 4 are very, very close in energy. Then what I have to do, I have to choose these 4 orbitals, which means 8 spin orbitals, and I have to choose 4 electrons as active, because this will be also lifted. These 6 will then be frozen. So you have to decide the problem, looking at the orbital energies. How many active orbitals you have to choose? But having chosen an active orbital, if you make a wave function which is a linear combination of all determinants that can be constructed out of the active orbitals, then it is complete, okay. Then such a method is called CAS SCF. If I make the determinants and then do exactly like MCSCF, which means I change the coefficients of this determinant, 6 determinants, as well as their orbitals. So in this case, the orbitals are, let's say, HOMO and LUMO, 2 active orbitals in this particular example. Then you change this and these orbitals, okay, and their coefficients of the 6 determinants in general. And of course, this is G and U, then you have only one determinant, okay, G square and 2 determinants, G square and U square, so just like this example. So in this example, it is a CAS SCF actually, because I have chosen only sigma U, I have 2 electrons. In terms of symmetry, this is the only possibility, okay. So in a way, this is a CAS SCF. So CAS SCF is like MCSCF, but the MC part is chosen like this, that you first look at the active orbitals, distribute the active electrons in all the active orbitals possible within the symmetry consideration, and then do an MCSCF. So that becomes CAS SCF. It is called complete active space and then self-consistent field theory. So basically just the MC space becomes the CAS, complete active space. After you do CAS SCF, there are many people who do within this multi-reference, multi-configuration function, another perturbation theory. That is very, very powerful, and that is usually called CAS PT, perturbation theory. So do a perturbation on CAS. So these are all methods that are available. In fact, many of you will see this. So you have a CAS and then do a perturbation theory. So you get CAS PT. So you can have CAS PT2, PT3, etc. depending on which order you do. Usually CAS PT2 itself is extremely time demanding, and people do CAS PT2 And you can see that first of all I have chosen the important determinants. I am doing a cast SCF, which means not just Ci, changing the orbitals, and then top of it I am doing second order perturbation where other orbitals will come. Because right now other orbitals are left out. I have taken only HOMO-LUMO. All these orbitals are left out in cast. Okay, so when I do cast SCF, remember the dynamic correlation from all these orbitals are left out. Only these two correlations are taken care, and this is usually called the non-dynamic correlation, where very few configurations are important. Now, I don't want to introduce these terms late in the course, but I just thought I will tell you. So, MCSCF or cast SCF does the non-dynamic or static correlation very well, but you need these dynamic correlations. All the other bases, then you have to do a perturbation theory on that, and that is where cast PD2 gives very good results. In fact, if you do second order perturbation, that's good enough. But in many cases, the dynamic correlation is not important. Only static correlation is important. Then you do cast SCF or MCSCF. So, these two kinds of correlations are very important, static and dynamic. So, usually static comes from a few configurations, few important configurations. So, in that case, you can do just a cast SCF. Dynamic comes from a large number of configurations, each of which is not very important. But their sum is. So, sum is important or sum cannot be neglected. So, I have to sum them also. So, this is what we have done so far. See, today what I am discussing right now, MCSCF, is really to take the static correlation. How do you take small number of correlation? And there you have a choice not to optimize the orbitals or to optimize the orbitals, but MCSCF does both. Okay, orbitals as well as then the coefficients. So, it is very good for static correlation. So, MCSCF or cast SCF, MC or cast whatever, SCF is very good for static correlation. This you have to do dynamic correlation, the perturbation theory, or normal CI, CI involving all other determinants. Basically, I have to involve the rest of the orbitals, not just those few configurations for dynamic correlation. So, this is something that is today understood, that the correlation also has two different parts, and different theories can handle each of these very well. So, I think this is something that I thought I would tell you among the other important theories. And there used to be also a theory which is almost now dead today, but it is a very important theory, which is called the electron pair theory, which actually started from Sinanoglu's work and then was eventually taken up by Wilfred Meyer as electron pair approximation, and there were several approximations, independent electron pair approximation and different versions of coupled electron pair approximation from SEPA 0 to SEPA 7. There are so many small modifications. This is called independent electron pair approximation, coupled electron pair approximation. So, take electron pairs, how do you couple them, the way you couple, but today the electron pair theory is almost extinct. Most people don't do it,